My name is Andy Robbins. This is Will Schroeder. Thanks for being here for our talk. Thank you, thank you, thank you. The title of our talk, An Ace Up the Sleeve, Designing Active Directory DACL-Based Backdoors. Quick information about me. My name is Andy Robbins. My handle is Waldo. I'm a co-founder and developer on the Bloodhound project. I've spoken at places, done training. If you really want to get me excited, come up and talk to me about the ACH file format, and we can talk offline about that.
Hi, my name is Will Schroeder. My handle is Harmjoy. I'm an offensive engineer at SpectreOps with this guy. I've written a lot of code. I helped write a good chunk of the Veil framework, Empire, PowerView, and PowerUp, if any of you guys use that, Bloodhound, Key Thief, and I really love Active Directory and dived into this research, and it's been a whole ton of fun. I've spoken at a few conferences. I'm a PowerSploit developer actively, and I'm a Microsoft PowerShell MVP, so somehow Microsoft doesn't hate me that much, I guess.
All right, so I'll give you guys a quick TLDR, where we are now, where we're going to be, and where we're going to wind up. So first, we're going to talk about DACLs and ACEs, what these are, how they work, why they matter. We're going to look at typical misconfigurations and how we can abuse these misconfigurations. We'll look at how we can analyze this stuff easily with Bloodhound from offensive and defensive perspective. We will look at designing ACL-based backdoors, and then we're going to show you some demos, some examples, some case studies, and then finally at the end, we're going to talk about what we can actually do about all this as defenders. So, an important caveat to keep in mind, we're not talking about O-Day, we're not talking about anything worthy of a CVE. Really, what we're talking about is how to abuse the existing Windows security model for malicious purposes. Thank you. Secondly, so we're not dropping O-Day. Secondly, we're talking about putting backdoors into an environment. Most of the time, you actually need to be already elevated to do that. So all the stuff that we're putting in, we're already domain admin, and then we're looking at, once we lose that, how do we get that back easily?
So why care about this? Some of the few things we think are really cool about this approach for persistence is, one, it's often very difficult to determine even if you find one of these misconfigurations, how do you tell if it's malicious? It could have been put there almost by accident from some third-party tool, a really old Exchange install, and a lot of the stuff we're going to talk about. These changes also will very often survive domain functional level upgrades and operating system upgrades. So there's remnants in a lot of domains of a lot of these misconfigurations. So a backdoor may have been put in 10 years ago in a really insecure environment, and even though the environment is more secured now, these could have existed for years. And we hope this kind of scares you. We're going to go in some background and stuff, but finally when we bring it all together, we hope the examples really kind of hopefully terrify a few people. So I love this quote from Matt Graber. He's actually up here in one of the rows. So as an offensive engineer, if you can dream it, someone has likely already done it. And that someone isn't the kind of person who comes that speaks at security cons like DEF CON. So we fully believe we are not the first ones to come up with this idea. We think that different advanced adversaries have almost certainly come to the same conclusion. So a big thing with this talk is we want to bring attention to the problem. The research isn't complete, but we're excited, and this may have already happened.
All right, so let's talk about some background. First of all, we need to acknowledge some existing work. First and most importantly is this French project from ANSI, which is the French equivalent of the NSA. The two guys who did this work, Luca Boyot and Emmanuel Gras, this is the Active Directory Control Paths project. If you haven't had a chance, I recommend you go take a look at it. We learned a lot about the Windows security model and DACLs and ACEs from their white paper. They also served as initial inspiration for using an attack graph to model out attack paths in an environment. So they served as initial inspiration for our Bloodhound project as well early on.
We also had to run their white paper through Google Translate because we're stupid Americans that can't speak any other languages. So we think we got all the details right. We got some cool stuff, but I'm sure there might have been some stuff we missed.
There's also this work from Robin Gramberg at Microsoft. This is the AD ACL scanner. Lets you do things like export ACEs to CSV. You can do basic diffing. If you want to know more about that, look at the TechNet link there. And the deck is obviously going to be online after. And then next, there's also this other project called BTA. Unfortunately, we missed this before our Black Hat talk. So this is from the team at Airbus for trying to get a wrangle on Active Directory ACEs as well.
One thing to note, they do some really cool analysis, but you need an offline ntds.dat. In our case, everything we're showing will be done remotely through LDAP, wrapped into PowerShell, but there's other weaponization methods, obviously.
So when we first started looking at this, we've had the idea, like, how can we implement backdoors that abuse Active Directory object control? We scoured the internet as well as we could. This is the closest thing that we could find. It's a blog post from 2010 written in Russian, obviously. This was all we could find. And we figured, like, if the only thing we could find was written in Russian, we were probably on the right track. They also, in this blog post, this guy also talks about hiding the existence of Active Directory principles, which we built on, and I think we improved on in a couple of different ways. So yeah, check out that blog post and run that through Google Translate.
Cool. So we're going to go into a little bit of technical background. I know this might not be as super interesting, some of these few slides, but you really need some of the background in this stuff to understand why and how these backdoors work. So, secureable objects in Windows. A secureable object is defined as pretty much as an object that has a security descriptor. This is a breakdown of the binary structure. So there's a lot of pieces to this, header bits, all this kind of stuff. All of this can be expressed as an SDDL, so a security descriptor definition language string. If you guys have ever seen that, we're not going to really kind of cover that too much. The pieces we care about are the owner, so the SID of the owner that for a particular object, and we care about the DACL, so the pointer to that DACL here at the end. So if you're not familiar with Active Directory, you're not familiar with the access control model, people throw around ACL, DACL, SACL, and all these types of things. People often use them interchangeably as well. So essentially, the access control list, the ACL for an object, is basically shorthand for the DACL and the SACL superset. So the discretionary access control list that you saw on the last slide, and the system access control list, the SACL. These are ordered collections of access control entries. So it's a pointer from the binary structure in memory to an array of these access control entries. The DACL specifies what principals, or trustees is another term, have what rights over the object. Nothing crazy, right? The SACL allows for auditing of access attempts to the object. We're not really going to dive into SACLs. We're going to cover a little bit at the end, but in this case, we're just going to mostly cover the DACL. So in an access control entry, there's some bits, there's some 32-bit fields that control kind of some auditing kind of components. There's a lot of stuff in there. What we really care about are, one, it's the owner, or sorry, the principal that has the rights over this object for this particular entry, and then the access mask, which is a 32-bit field that defines what those rights are. This is what it'll look like in ADUC and Active Directory users and computers. So you can see that the principal is, up there all the way at the top right, the object is victim, so victim user. The principal is harmjoy, so harmjoy has these rights. There's lots of rights in there, and the ones we care about are, like modify the permissions on the object, modify the owner. So again, this is just the access mask. There's one bit in the access mask that we particularly care about. So in those kind of like the control bits in this ACE entry, with this access mask, there is a DS control bit. So this is interpreted in one of two ways. So if the target GUI, or the target GUID for the object ACE type for that particular ACE is a confidential attribute. So the most common case is lapse, right? So you don't want everyone to be able to read that lapse password, and we'll go into lapse in a little bit. If DS control access is flipped, then that grants read access to that confidential attribute. So that's one particular way to interpret it. The second way is extended rights. So if the object ACE type GUID matches a registered extended right that is registered in the forest schema, say user force change password, or DS replication get changes and replication get changes all, so these are DC sync rights. So if those are registered in the forest schema already, and that GUID is resolved and actually points to a particular extended right, then flipping the DS control access will grant a control access right for this. So it's the way that extended rights are granted. And extended rights are just a way to, like I mentioned, extend the actual generic rights that are available in that 32-bit access mask.
Okay, so the part of the operating system that is actually in charge of evaluating these ACEs in what is called canonical order is the kernel mode security reference monitor. So the SRM takes an access request for a given principal against another object, and it evaluates the DACL in that canonical order to make an access decision, whether access is allowed or denied. Importantly, we can abuse this function of SRM to hide principals or to hide the existence of DACLs. The way that we do this is we abuse the fact that explicitly defined aces on an object they always take precedence over inherited aces. So let's look at an example here. We have this OU called IT. And on that OU, I'm going to specify an explicit deny ace. Let's say it's just for full control. That's going to inherit down to the OU that is contained there called help desk. And then the Robbie Winchester user at the bottom of this OU tree also gets this ace inherited down to it. Well, what if I put a conflicting ace in the intermediary OU? So at help desk, I say, well, wait a minute, I want to have an explicit allow. The explicit allow takes precedence over the inherited deny, even though typically denies are given precedence over allows. Finally, on the Robbie Winchester user, I specify two explicit aces on there, an explicit allow and an explicit deny. So the order that you see on here is what is called the canonical order, and is based on inheritance from parent and grandparent OUs. So the explicit deny will be evaluated first, then the explicit allow, then the inherited allow, and then finally the inherited deny. The green inherited allow on Robbie Winchester is given precedence over the other inherited ace because generationally that OU that it inherits that ace from is closer. So let's look at some typical DACL misconfigurations for how we can do object takeover and how we can abuse these. Another caveat that I'll remind you of, we're talking during this talk primarily about persistence. We're not looking at privilege escalation for this talk. We do have content on my blog if you want to read about that, but the primitives for object takeover are going to be the same. Additionally, we're looking at chaining together multiple different control relationships between different principles to make this very, very difficult for a defender to find. So you have user objects and Active Directory. How can we take over a user object by abusing these access control entries? There are two primitives that we have for you. One, we can do a targeted Kerber roasting attack. By a show of hands, who knows what Kerber roasting is? After our talk is done, go read Sean Metcalf's blog about Kerber roasting. It's going to change your life. So basically, we can set a value on a service principal name for a user, and then we can request a Kerber roast ticket back from the domain controller for that user as any other user, and then we can crack that ticket and recover that user's clear text password. Anybody in the domain can do this. Secondly, we can change the user's password without knowing its current value. This is the privilege that you give your help desk so that they can change people's passwords after they fat finger and lock themselves out. At the bottom here, we have two power view commandlets that can abuse these: set domain object owner and set domain user password. There's also one for setting a user SPN. How can we take over a group object? Well, what we're interested in is not necessarily the group, but we're interested in the privileges that the group has. So if we have the ability to add an arbitrary user to that group, we can give ourselves the same rights that that user has and write that existing privilege forward. We can write property to all properties to do this, or we can have write access only to the member property, and we can add a user to that group. In PowerView, you do this with add-domain group member. For computer objects, this gets a little bit tricky because the only thing that we know of right now is being able to abuse a lapse installation. And so if our user has the ability to read the local admin password attribute on the computer object, obviously we can pivot to that system and we can be a local admin. If you have other ideas about this, we are very, very excited to hear it. We are all ears.
One thing to note as well is we are not claiming that this kind of taxonomy is complete. These are some of the primitives that we found that we've used, operationally, but we know for sure there are other types of object takeover relationships. So the point of this talk is not to show you every way to take over any object. It's to show you chains of these kind of interesting backdoors.
Next, domain objects. So even though I'm not a local admin on a domain controller, even though I'm not a domain admin, if I have full control over the domain object, which represents the Active Directory domain, I can DC sync. DC sync, if you're not familiar, allows me to remotely request an NT hash for any other user in the domain if I have that privilege.
Thank you, Benjamin Delpy and Vincent Letou, for DC sync.
Yes. So the two explicit privileges that we actually need for this, we don't need full control of the domain object. We need DS replication get changes and DS replication get changes all. Then we can request NT hashes for any user, including the curb TGT, which is interesting, and we'll show you why later.
So, group policy objects. This is one of the few relationships that we don't have incorporated into the Bloodhound schema yet. These are going to have to write a custom pathfinding algorithm to handle all the weird inheritance issues. What the main takeover primitive is, can you modify the GPO? You can modify the GPO. These GPOs are linked to OUs, sites, and domains, and there are users and groups and computers contained within these. So if you can modify the GPO, there's 1,000,001 ways that you can get code execution on a computer it's applied to, or you can get essentially code execution in the context of the user that the GPO is applied to. So the rights we care about here are write property to all properties, like some of the other examples, and write property specifically to this GPC file sys path. This represents the rights to actually modify the GPO, and if you modify the permissions on this, those permissions will actually be cloned down to the file system in sysvol. So if you have the rights, or modify the rights, then you can just go straight to sysvol and modify any of the GPO settings. There's a set of a few rights that apply to pretty much all the objects. So generic all, this will grant you all generic rights like we mentioned. It also covers some of the control or object takeover rights that we're going to cover in the next slide. Generic right allows for the modification of almost all properties except for those confidential properties handled by that DS control access bit. These are abusable power view set domain object. Again, this is how you could do that targeted Kerber roasting. And again, these rights normally apply to most objects for takeover. So, control rights. These are rights that allow a principal or trustee to take control of a particular object. So, if you have write DACL, you have the ability to modify the security information for an object. You can add whatever new ACE entries you want, so you can grant yourself whatever rights. So if you have write DACL in the domain, you can grant yourself DC sync rights. And again, that's abusable with add domain ACL. With write owner, owners have implicit full control of the object despite any existing, deny ACEs or anything like that. This will come into play when we actually want to hide the DACL and things here in a little bit. So this is also available with Power View with set domain object owner.
Okay, so let's slow down for a second. Let's do some visuals to kind of make sense of what all we're talking about. We're going to look at some analysis that we can do with the Bloodhound interface. We added several of these ACE edges into the Bloodhound database so that you can hopefully easily map out what these existing control relationships look like.
That's the 1.3 update that happened just about a month or two ago.
So for defenders, we hope that you guys can use this for enforcing your least privilege policies, for identifying what ACLs may be misconfigured and giving people more privilege than they actually need, and then detecting some of the more non-stealthy DACL-based backdoors. As an attacker, we can use this to find ACL-based escalation paths. We can also look for principles that are interesting for us to backdoor based on the existing privilege that they have. And then we can also kind of understand the existing situation there is with ACLs and, do we really care about being sneaky in the first place? So this is the Bloodhound interface. The default view, we see the domain admins. We'll click on the domain admins group and we'll look at inbound object control. So who has control of this group? From the first degree perspective, we see there are 6 groups that have control over the domain admins. Several of them are generic all privilege, and then one of them is write DACL privilege. You may notice that a lot of these are exchange groups. These groups also include other groups and computers and users. So if we unroll this out, we can see that there are actually, in fact, 29 principals that have full control of the domain admins group because of security group delegation. Now, what if I want to unwind this out and say who can take control over all these principals? What we call this is transitive object control, or an ACL-only attack path. I can do that with Bloodhound after I finish doing this right here and showing you the group delegation. So let's go back into inbound object control. Transitive object controllers, there are actually 50 of them. So there are 50 objects that have an ACL-only attack path to be able to take control of the domain admins group. These users here all belong to a group called identity administrators, which is a member of this group called account operators that has force change password over this user, which is a member of the domain admins group. So let's look at something a little more interesting and complex. This user here belongs to a group, which also belongs to a group that can change this user's password, who can change this user's password, who's a member of this group, who has full control of the domain admins group. So that's inbound object control. What we can also easily audit is outbound access control. So for a given principal, what privileges do they have against other objects? So I'll find this user here called rTaylor and go to outbound object control. First degree object control, it's 0, because that user itself is not specified as a principal having privilege against another object. For group delegated control, there are 4 users that he has the ability to take control of because of security group delegation. What I can also say is transitive outbound object control. So if I can take over any of these 4 users, then what? What can I do? Bloodhound finds this easily, and I see that for transitive object control, I have control over all these principals here by ACL only attack path. So this user belongs to this group, belongs to that group, who can change that user's password, who's a member of that group, who has control over all these other users here. That's it. All right. Thanks. Pretty good on time. So let's look at how we can actually design backdoors based on these principles. So what our objective is, we want to be able to get back into an Active Directory environment on any computer and be able to instantaneously escalate our privileges back up to whatever we want. Maybe that's enterprise admin, maybe it's domain admin, maybe it's local admin on a system. We want to be able to blend in with normal ACLs that already exist in the environment. So let's see what we can come up with. So how can we hide the DACL? I just showed you with Bloodhound how we can audit the DACLs, but what if I don't want you to be able to audit the DACL as a defender? This requires 2 steps. I change the object owner for the object I'm backdooring away from the domain admins to another principal that I control, or the principal itself.
And remember, that's because object owners have implicit full rights despite any explicit denies that might exist in the chain.
Secondly, I will add a new explicit deny ace, which recall will take precedence over anything else in the DACL. And I say the everyone principal is denied the read permission privilege. Then I can't audit the DACL from any other principal except for the one that's backdoored. Here's what it looks like in ADUC GUI for setting this. So I'm saying the principal everyone is denied read permissions. It's that simple. I can also hide the existence of a principal that I'm backdooring. And this requires 3 steps. First of all, I need to change the object owner because owners also always have full control. Then I'll grant explicit control either to the object itself or another object that I control. And then on the OU that contains this user or group or computer or whatever it is that I'm backdooring, I'm going to say that everyone is denied the list contents privilege. Then when they try to look up that user in ADUC or by LDAP or with a net executable, they can't see it. Here's what that looks like in ADUC. I assure you there is a user in this OU. You cannot see it.
And these stealth primitives we're going to factor into some of the case study demos at the end of the presentation.
So to summarize, we know how we can abuse ACEs to take over other objects. We know that we can control who has the ability to audit the DACLs. And we know that we can hide the principals and trustees from easy identification.
Cool. So remember that quote. If you can dream it, if you can imagine it, it's probably already been done. We're going to go over 5 case studies that we were able to come up with in the course of this research. We're 2 guys in a basement just figuring this out for the first time and thought for about a week what some cool stuff we can do. If you actually had people much smarter than us with a lot more money and time and funding, I'm sure there can be even more subtle and kind of crazy things you can do with this. So the first one, like we mentioned, you don't need to be domain admin to DC sync. DC sync is entirely dependent on 2 ACEs on the principal domain object. And again, all domains a domain is actually represented as a domain object in Active Directory. So if we, to implement the backdoor, and these will all kind of follow the standard of we'll show how to implement the backdoor, and then we'll show how to execute the backdoor. So if we add manually DCC, DS replication get changes and replication get changes all rights to the domain object, then this user, who's the attacker-controlled user, who's not in any privileged groups, just stock, just created user, has the ability to DC sync any user's account forever, unless defenders actually figure out these rights in the domain object and actually remove them.
So one thing to add to that is you can do DC sync remotely. You don't need code execution on a domain controller. So you can do this from any domain joint system.
Here's a video. So okay, I'm going to go ahead and import Power View. And then the bad guy user is going to be our attacker kind of control principal. I'm just going to show that the bad guy user is not in any privileged groups. It's brand new. We're going to save the SID for the bad guy user off. And then next we're going to use, and again, all this Power View stuff, we're going to use an ACL enumeration commandlet and show you that there are no explicit aces on the object where the bad guy is the principal. Then we're going to use add domain object ACL, and we're going to grant DC sync rights. You could do this in your lab tomorrow. So we're going to add those, then we're going to enumerate those rights again and just show you that these new explicit aces have been added. You see, okay, there's the SID for that bad guy user, and he now has these DC sync replication rights. Cool, cool. Now we're going to pop up a window that had, it's a little small. We had a window running as bad guy. We tried to DC sync previously. We're going to try it again, and now we have DC sync rights, despite them not being in any privileged group. So starting simple, nothing too, all right. Thank you. This is a pretty simple example of an DACL-based backdoor, and we're going to get a lot more complicated. So admin SD holder. I don't have time to completely go into this. There's also a good time to note that we gave this presentation at Black Hat, and we wrote a 64-page white paper that goes into excruciating detail for all these things. That will be released through Black Hat and also through our website at specterops.io. We're going to release it probably next week. So if you are interested in this stuff, there's going to be tons more background and examples and mitigations and all that fun stuff. So 30-second summary, admin SD holder essentially acts like a permission template for highly privileged groups. So to implement the backdoor, the attacker grants themselves force change password or generic all rights to this CN admin SD holder system. This object exists in every single domain, so they add it to the object itself. Then every 60 minutes, a special process called the Security Descriptor Propagator Process, or SDProp, will run. It'll enumerate all the privileged groups like enterprise admins, account operators, domain admins, and if the permissions on those objects differ than the template in admin SD holder, it takes the permissions from admin SD holder and then imprints them onto the secured, highly privileged groups. Then the attacker hides their principal using the methods described. We don't want to hide the DACL here because this is going to be cloned off into every domain admin and enterprise admin and all that kind of stuff. But we can complicate it and we can make it kind of look like an orphaned object. Then to execute, the attacker force resets the password for any account that has admin count equals 1, any privileged account. And we have a demo for this too. Okay, I'm going to load up Power View again. Again, I'm not on a DC. I do have domain admin rights. Oh, I'm going to show the bad guy user's OU location. He's in the OU totes not evil because that's a good way to hide. Totes not evil. Then we're going to add all rights for this bad guy 2 principal to the admin SD holder object in the current domain. Now, that was the actual backdoor. Now we're going to hide the principal. We're going to change that object, that bad guy 2, we're going to change the owner of that to himself. And then we're going to deny, one second, we're going to get some of the raw objects we need to do some of this manipulation. We're going to deny everyone the ability to read the permissions on the object. Or we're going to do a complete generic all deny so no one can actually do anything on the object. And then we're going to deny everyone the right to list the children of that totes not evil OU. So this is completely hiding the principal. Commit that all off. And we could have run all these commands, in 3 seconds. Then we're going to wait 60 minutes for SDProp to run. We're back. We're going to check if the rights propagated. So we're going to enumerate the rights for a particular domain admin. And we see the SID, that bad guy SID, shows up for generic all. But if we try to actually enumerate the bad guy 2 user, we can't find it through LDAP or DS query. Now we're going to refresh, and that guy disappeared, even though he's still there. So, there's ways that you could eventually, take these things back over, but it's hard to find. And now we're going to use that account to show force resetting that domain admin's password. Then we're going to do run as with CMD. And now we have codex as a DA again. Cool stuff, hopefully. I promise I'm not begging for applause. So LAPS, we don't have a demo video for this one, but we're going to talk through it. So LAPS is Microsoft's local administrator password solution. It's an awesome free thing that Microsoft released. It's a series of client-side and schema extensions that every 30 days, the computer will randomly rotate its local administrator password and then store it in this protected attribute, or this confidential attribute called MS-MCS admin password. So the LAPS also includes a series of commandlets released by Microsoft. So it's the admin password.ps commandlets. There's one particular commandlet called find admin password extended rights that audits who has the rights to read this particular attribute. We're going to show some issues with it, but I want to emphasize up front that these commandlets were not built as a security protection type thing. It was meant to find the results of who can actually audit these things based on the normal process that LAPS rights were delegated. But there's a few edge cases. So here's who can actually read admin password. We have some DS control and a whole bunch of like inheritance kind of issues. The above checks, also generic all, because that will imply that DS control access. Also, that object control stuff that we talked about. So are you the owner? Can you modify the DACL or can you modify the owner? This list is also not comprehensive, so the white paper was updated. There are several more flaws we discovered, just a few days before giving the presentation. These are the flaws. So if DS control access is flipped, but the ACE applies to all descendant objects instead of computer descendant objects, that's an edge case. Also, it doesn't check if you're the owner. If you can write the DACL, write the owner, and it only analyzes OUs and optionally specific computers. It doesn't check for things in the default, user and computer container. So here's a normal case. We have this John Smith user, and he is not able to read that LAPS password down there at the bottom. But if you run these find admin password rights, you can see he's not listed, so it makes sense. So we're showing that this user is not part of the server admins that pops up for this audit. Now, we're going to craft a very specific ACE that exploits the flaw with inheritance. So when we add this ACE, that particular John Smith principal will have the right to read the LAPS password forever, whenever it's changed, but the default auditing components released with LAPS will not find it. So this is a LAPS-based backdoor. And here you see it actually executed. So John Smith, he's not in server admins, but he's able to read the LAPS backdoor despite not actually showing up in the default auditing commandlet. So cool. We think these issues will be fixed pretty soon. It was just, we dove pretty deep into some of the LAPS information, and again, a ton more in the white paper.
Okay, so
this is my favorite.
Yeah, it's mine too. I'm a little bit biased though. So we mentioned how third-party applications can extend Active Directory schema. They can add security groups. They can add control from groups to other principals in Active Directory. By far, the biggest offender of this is Microsoft Exchange. So with Microsoft Exchange Server 2016, 2013, and 2007 SP1 and forward, Exchange Server will create a group called Exchange Trusted Subsystem and add all of the Exchange servers into that group. Then it will grant that group full control over every other object in the domain, with the exception of accounts whose DACL is protected by the admin SE holder object. Before 2007 SP1, this also included full control over everything. So essentially, an Exchange server had the same privilege that a domain controller did.
So if you're ever on a pen test or red teamers, if you ever end up popping an Exchange box, you are probably 1 or 2 hops away from compromising the entire domain.
There are several real environments that we've gone into where what we have seen is reality is that the Exchange Trusted Subsystem does have full control of everything. The domain object, domain admins, domain controllers, enterprise admins, you name it, Exchange owns it. So for this, we're going to go through a couple of steps to implement our backdoor. First of all, we want to find an object that we can backdoor that is not going to be very obvious for an auditor to find. So we're going to ride existing privilege by finding a group that already has admin rights against one Exchange server through group delegation. So not just one that is like, if you did net local group administrators and you found that group, we're going to go further back. Then we're going to grant authenticated users full control over that security group. We're going to change the group that we're backdooring to the Exchange server. And then we're going to deny read permissions on that group to the everyone principal. How do we execute this? We're going to regain access to Active Directory as any user on any computer. We're going to add our current user, because they are an authenticated user to the domain, they have full control over the security group like everybody else. We're going to add ourselves to that group, and then now with our newfound local admin rights on an Exchange server, we're going to use psexec, thanks Mark Kusinovich, to execute Mimikatz as the system user on that computer. When you execute as a system user on a computer, you have the same privileges that the computer object in Active Directory has. So a lot of times this means DC sync. So we're going to go into Bloodhound and we're going to find the group that we're going to backdoor. So we'll go to domain admins and we'll look at what other principals have control over the domain admins group. We can see that the Exchange Trusted Subsystem has full control over the domain admins group, and there are several computers that are added to the security group. We're going to select one of those. We're going to select Exchange 001, and we're going to see who the existing admins are on that box. Through Bloodhound, we can automatically unroll out who all the effective admins of a system are by group delegation, and we can see there are 7 users that have local admin rights on the system. There's a system on the right. That group is explicitly an admin. That group has a group there, and then this intermediary group also has a group called Server Backup Tier 2. This group, even though it would never show up in the local admins group on that system, is a local admin. So we're going to backdoor that group. First, we're going to import PowerView. Then we're going to get the raw directory entry for the object. So Server Backup Tier 2, the group. We're going to grant authenticated users full control over that security group. It's done. Then we're going to change the owner of the group to an Exchange server, just for anti-audit reasons. That's done. Then we're going to deny read permissions on that group to the everyone principals. You can't easily audit this backdoor. And that's done. The backdoor is in. How do we execute this? We regain access to the environment as any user. Domain user, you're not an admin anywhere. Again, we're going to import PowerView, and then we're going to add ourselves to that security group, Server Backup Tier 2, which is now done. Then we're going to use psexec to remotely run Mimikatz as a system user on that Exchange server. And then we're going to DC sync the kurbtgt user, which we can then use to create a golden ticket, and then we effectively then own the domain. And it's done.
Cool. Exciting. Love those curb hashes. So this last one we don't have a video for. It's also the most complicated. But again, it's spec'd out in even more detail in the white paper. So the entire backdoor consists of an attacker grants him or herself generic all to any user object with the attacker as the trustee. And then you kind of grant that patsy or proxy user the right DACL privilege to the default domain controller's GPO. That's the entire backdoor. And this is kind of a separate approach that we talked about in the paper of using, all right, a proxy or patsy type user instead of the actual attacker principal. So to execute it, get codecs in the system again, you force reset the proxy user's password, you use that authentication context to add a DACL to that default domain controller's GPO that grants, you're adding a DACL to the GPO that allows write access to that GPC file sys path. So we are granting ourselves the right to edit the GPO itself. Then we're going to grant, through modifying the GPO, the SC enabled delegation privilege. This is going to be pushed down to the domain controllers, and what this does is it allows us to modify the MSDS allowed to delegate to super protected property on user accounts. And the reason it's protected is if you're able to modify that, you can re-compromise the entire domain at will by executing essentially a constrained delegation attack through using Mimikatz and Kikyo. This is pretty complicated. I have some stuff in my blog in the, earlier in January that goes into this more detail. But cool stuff. Pretty subtle though, right? It's just one user that's not the actual attacker. Then you have generic all on that, and you use that user as a proxy to add the rights you want. So what we can do in the future is actually do really kind of crazy chains of this going all the way back. So not only if they find the back door, they have to walk back every possibility of someone that might have had access or could gain access to that object. So this is, again, kind of an anti-incident response measure. All right, so defenses. All is not lost. We promise. The problem with these backdoors is you have to have event log auditing turned on at the moment the misconfiguration is introduced. So if this was introduced 10 years ago and you didn't have this stuff tuned up, or you don't have 10 years of event log data, which I don't think many people have, then you're not going to figure out who actually put this stuff in, assuming you can find it and assuming you believe it's actually malicious. This is why we think this is a pretty cool persistent strategy. But for example, if you want to stop these from being put in the future, there's different event log IDs, like 4738, a user account was changed, and you can filter these by the particular property modified. And you don't have to monitor for every single possible change. You just need to start monitoring piecemeal by all these kind of object takeover primitives that we talked about. And I'm also going to be putting out a blog, and hopefully in the next few months, that gives complete defensive guidance for every single ACL-based takeover primitive that we covered. Okay. So replication metadata. Metadata remnants from a domain controller are actually preserved in these particular properties in Active Directory. So when the DC synchronize everything, there's this XML-based metadata that you can pull out. So you can figure out when a given attribute was modified, and from what domain controller the modification originated from. So this kind of points you in the right direction, but you have to go to that DC and parse those event logs to actually figure out who actually made the change. And I have a draft post that I'm going to drop that goes into the replication metadata for hunting in a lot more detail. Also SACLs, so those system access control lists that specify the types of access attempts that generate audit records in the security event log of a domain controller. SACLs have been around forever. People don't really use them because if you turn them on, there are going to be tons and tons and tons of events. But we really think that if you implement SACLs, again, just for the object takeover primitives that we talked about, you can cut down a couple orders of magnitude in the amount of noise and actually just, really pay attention to the good stuff. And there's a bit.ly link that has some more information on there. Future work, we worked really heavily with Lee Christensen, Tifkin on some of this stuff, and we tried really hard to set a null DACL or otherwise manipulate the header control bits like SE DACL present. So the idea being, like you can do on a host, setting a null DACL so anyone in, anybody, authenticated users could have access. But any attempts to set the NT security descriptor remotely on an object were ignored. But this warrants another look. We weren't able to get it working. The documentation said why, but there might be a way to do it. We also want to research additional control relationships, particular those takeover primitives for computers, as well as SACL type auditing. So credits, we want to special thanks to all the people who helped us with the slide deck and research. Definitely Lee Christensen, Tifkin, he really helped us. Jeff Demick for content review, everyone else at SpectreOps, and also Matt Graber, who used to work with us, gave us some really good feedback and some really good feedback and kind of content review. So with that, we're pretty much done. We can have a few questions, and if we run out of time for that, we'll be outside.
Awesome white guy.